the definition, like we just said, of mass that we are going to be using, it's the amount of matter in an object. Sort of how much stuff is in there. Now, as I'm passing around these metal solids, those of you that have seen them, how does the volume of them compare? Katie?
Silver one was a lot lighter.
The volume of them.
They're all the same.
Yeah, basically, these metal solids all have the exact same volume. Okay, they're all same length, width, and height. Okay. But as you are passing them around, what did you notice, Katie?
The silver one was a lot lighter than the other one.
The silver one feels much lighter. Silver one has a much lower mass than the solid chunk of gold that I'm passing around, or the copper, or the bronze. So why? That's the question. Why does one of them feel lighter than the other? Why does one have much more mass if they're the same volume? Joey? Yeah, because in the heavier ones, the ones with more mass, there's more matter compacted into the same volume, giving it a greater mass. So mass is how much matter there is in an object. So it's not the same as volume. Volume is the amount of space. Okay? How much matter you're packing into that space determines the mass of the object. And we have in science this law that's important, called the law of conservation of matter and energy, really, as well. We're just going to talk about the matter part for right now. If I take this water that's in this graduated cylinder, it has a certain mass, certain volume. If I put it into a pan and boil it away, am I destroying the water? Are the water molecules gone?
No.
No. Well, what happened to them? They're not there anymore. Grace?
They evaporated.
Right. They evaporated, but they're still water molecules. I haven't destroyed them. If I take a piece of wood and I burn it in a fire until it's just ash, did I destroy the molecules that made up that original piece of wood? No. I've transformed them. Much of that matter turned into carbon dioxide or carbon monoxide that escaped in the atmosphere. But the actual matter, okay, is still there. The actual atoms of carbon and hydrogen and oxygen, they're still there. I've just transformed them into a different form. Okay? So the law of conservation of matter and energy tells us that matter cannot be created, cannot be destroyed, but it can be what? What term could I use? Dean? Converted, transformed, changed. So we can change matter, we can change molecules, combine them in new ways, but we can't create or destroy matter or energy. And that's what we call the law of conservation of matter. So we're going to be studying mass and the metric units for mass. The base unit is a gram. Bless you. Everyone see these metal? Yes. So the base unit is the gram. A gram is about the mass of like one of these like little pens. About the cap of this pen will be maybe about a gram. There's a kilogram. It's the other unit we often will use. A kilogram is about 2.2 pounds. Okay. So if you were to define your weight in kilograms, it would be, about half or more than half what your weight is in pounds. The other unit that we'll see, we won't really use much in class, but you will see, are milligrams, 1/1000th of a gram. Where will you see milligrams used in your sort of everyday life? Grace?
If you're measuring something really small.
Yeah. Where might you see this all? Where did you maybe see this this morning? Anyone see milligrams as a unit on something? Come on. Okay. Anyone see milligrams anywhere this morning? Where?
Like food.
Okay. If you were like sitting there eating your Fruity Pebbles, looking at the box of cereal, what you might find there is it might tell you the amount of sodium in that cereal. And that would be measured in milligrams. Does anyone take a vitamin each morning? You ever look at the bottle of vitamins? It'll tell you how much vitamin C, how much vitamin D, okay, how much niacin, and so forth, and it will give you those in milligrams. If you ever take any type of medication, okay, usually dosages on medications are given in milligrams. You may take 200 milligrams of ibuprofen if you have a headache, okay? So often medications, nutrients are measured in milligrams. It's a small unit, but we only require small amounts of certain nutrients, and medications are usually given in smaller amounts. So that's where you'll see milligrams.
Well, like, doesn't it usually go, like, on the box, like, the nutrition facts or whatever, it says it in percent?
Yeah, that's percent of what you're supposed to be getting per day, and it usually also will give you the actual amount. So it gives you as a percentage, and often it will give it to you as a an amount. For example, if I look at one of these noodle soups, so it's telling me in this there are 920 milligrams of sodium. That would be about 38% of what you're supposed to get in a day. So if I eat this ramen, and that's almost half of my sodium for the entire day. And again, it tells you total carbohydrates 40 grams, fiber 2 grams, and so forth. So it gives you in both. So some nutrients it tells you in grams, those are the ones there's more of, and some in milligrams, depending on what it is. All right, so to measure mass, we use a couple tools. In class, we'll use two different tools for measuring the mass of an object. We'll use a triple beam balance, or you might use a digital balance. Okay, so I'll tell you about each of those. So have you guys used a triple beam balance before? No? Okay. Well, some people have. In elementary school, you measured mass before, right? You use those hand?
Yeah.
Okay. Works on the same concept, really. A little different. So in this triple beam balance, the parts you have, and you could label these on your diagram, the part where you place your object is called the pan. These weights that you slide back and forth, they're called the riders. Beneath the pan, there's a knob that's called a zero knob. And then there's, on the arm of the balance, the pointer. So that's the balance, called the triple beam balance, because there's three of these beams, we call them, that have markings on them indicating mass. Okay. The riders, you slide them. The largest rider indicates 100 gram units, and there's a notch. Okay. So when you're using the largest rider, this weight has to be in one of the notches. Same thing, this is the 10 gram rider. You slide it over, it has to be in a notch to measure accurately. The smallest rider that measures single grams and tenth of a gram on this balance just slides freely. It doesn't have to be in any notch at all. Okay. And so the first step in using a triple beam balance when you're going to use it tomorrow in class is to zero it. And what that means is you have nothing on the pan. And if there's nothing on the pan, all the riders are set all the way to the left at 0, then this pointer should line up exactly at this 0 mark. Does it, Joey? Is it right on the 0?
Yeah.
Okay. If it were not, I would adjust this 0 screw over here. If I turn it up, it'll raise the rider up a little bit. If I turn it down, it'll move it down a little bit. So you just adjust that a little at a time until the pointer is exactly at 0. Okay, that's going to ensure that you're going to have an accurate measurement. So you adjust it using the 0 knob. Then you simply take your object. I'll take this lump of gold, put it on the pan. Obviously, once you place something on the pan, the arm goes up because of the mass of that. And then you start to move these riders until the pointer points back at 0. You can start with the largest rider. So if I slide it over to 100 grams and the pointer goes all the way to the bottom, what does that mean? It's less than that, so I have to go back. All right, so then I can move the 10 gram over. Okay, if it's done, once I slide it goes all the way down, what do? Back it up. Back it up. Okay, so I know it's somewhere in that vicinity. Then I move the smallest rider until it balances out and goes to 0. Once you're getting close, you have to wait a little bit, let that balance out. Still not there, right, Joey? See if I got it there. Sometimes it's easier to use your pen to move that, slide it a little bit. That's right at 0?
I mean, it's like half a centimeter off.
All right, so we want to be right on. So I need to go back a little bit more. So if I slide it just a tiny bit, once it's all balanced out, then I can figure out the mass. Is that good? All right. So now once it's completely balanced, all I need to do is add up the riders. So the 100 is still at 0, so that doesn't come into play. This is at 60. The smallest rider is 0.9? So yeah, you gotta kind of be close to read it. Yeah, it's 0.9. So 68.9 is the mass of this. So that's how we use the triple beam balance. Does anyone at your doctor's office still use like the old school, like you stand that thing and they slide?
Oh, yeah.
That's a triple beam balance. It's obviously has different weights on it and so forth, different leverage, but it does the same thing. They slide that thing over until it balances, and that's what your weight. They're really measuring your mass when they're using that.
Are they as accurate as like the digital ones?
Yeah, they're just as accurate. If it's calibrated well, they're just as accurate, yeah. All right, we also do have the digital balance here that we sometimes will use. Digital balance, obviously, it's a little easier to use. You turn it on, and once you turn it on, obviously, if there's nothing on the pan, it should read 0. If it doesn't, there's a 0 button you can press to reset it to 0. You place your object on the pan, and you read the display. It says 68.8 grams. So a little discrepancy about 0.1 grams. I don't know which is the more accurate of the two, but there's some error when you're using these tools. Oh, now it says 68.9. So that's how we use this. This only gets accurate to the 10th of a gram. So this is not a balance we could use to measure 10 milligrams of something. It's not accurate enough. You can buy balances that are much more precise, that you could measure things to milligrams. Just depends on the balance you have. These are relatively inexpensive for use in school. Now, that's how we use it. The parts of it are the pan, obviously, the 0 button, and the display. Not all that complicated. Now, what if I press the 0? What if I keep this weight on here and press the 0 button? It's going to say 0, right? Now, what if I take the weight off?
Maybe negative.
Yeah, it's going to give me a negative number. What should it be?
Negative.
Negative 68.9. Now, the other thing is that often we may want to measure the mass of a liquid, which presents a little bit of a challenge. If I want to know the mass of 10 milliliters of this liquid, I can't just pour 10 milliliters on the pan and measure it. So what do I need to do, Stephanie?
You need to measure that first, and then pour the liquid into it and measure it, and then subtract that with the liquid.
Exactly. I need to first find the mass of my container, record it. Then I add my liquid, find the mass again, and then subtract the two to find the mass of the liquid alone. Now, I also could do it another way. You know how, Carter?
You put the cylinder on the electronic one, and then you'd zero it, and then you would pour the water in, and it would give you the...
Exactly. So if I put my graduated cylinder on the electronic balance, 132.3, but then I zero it, it'll say 0. Now I can add my proper amount of my liquid, and it's going to be telling me just the mass of the liquid that I added. So it's just another way to do it. Either one would give you the right answer, but that's how we can do that. All right, let's just look at a quick example. If I look at a triple beam balance here, and the riders are in these positions of these green shapes, what mass is this showing? I know they're not lined up perfectly, but what mass is being shown here? Priscilla?
175
175 tablespoons of hummus.
grams.
Right. And how about this next one, Jake?
328 grams.
328 grams, correct. So I just add up the riders to give us. And now on this actual triple beam balance, often this rider will be between whole numbers. There's markings for every tenth of a gram, so you can be accurate with that triple beam down to the tenths place. All right, the last thing for us to talk about today is this concept of mass versus weight. And usually in our everyday language, we use them interchangeably. We talk about mass and weight as if they're the same thing. But there actually is a difference scientifically between mass and weight. So we know that mass is how much matter is in an object, how much stuff is there. We just talked about that. And, you know, if I take this chunk of gold to the top of a mountain or to the planet Venus, is its mass going to change?
Yeah.
It is?
No.
It's not?
Wait,
Well, some of you say yes, some of you say no.
No.
Is its mass going to change when I take this to Venus?
No.
Why not?
Because you can't change math, or you can't give it more or less.
Well, you could, but I'm not, right? So it has the same amount of matter in it no matter where I take it. Okay. And we measure mass in grams. If I find the weight of this then, so now we're going to talk about weight. So how is weight different? Am I?
Weight is dependent on gravity.
Yeah, weight is not the amount of matter in an object, but it's how much is gravity pulling on that mass. So that's a slightly different concept. It's related to the mass, but it is also dependent on gravity, the force of gravity. This formula sort of got put in the wrong place a little bit. It should be up here. So when we're finding the weight of an object, we use its mass, but we have to multiply that by the force of gravity. And the force of gravity changes depending on several factors. And technically, the units that we use in measuring weight, because it's a force, is a unit you're probably not familiar with. The units that we use are named after famous scientists. You know who it is, Joe?
Albert Einstein.
No. It's not. We don't measure weight in Einstein's. We do measure it in Newton's.
Oh, stupid. I was thinking the mass times gravity.
Okay. So Newton's named after? Yes. Studied lots of stuff,
Yeah.
including gravity, mathematics.
Doesn't an apple fall on his head?
That's what people say. I don't know if that's an actual true story, but yeah, Apple found his head and that helped him arrive at his ideas regarding gravity. I don't know if that's actually true. But yeah, the units we use for weight are newtons. So right now, obviously, there's a force of gravity between me and the Earth. Technically, any two objects in the universe exert a force of gravity upon each other. So when you jump, okay, there's a force that attracts you back down to the Earth. But, you may not know this, there's also a force between you and the Earth, okay, which attracts the Earth to you. Now, which one actually moves?
You.
Why?
Because you weigh less. If you weigh,
Right.
like, so that's why the Earth is attracted to the sun, because the sun weighs more.
Yeah.
If it wasn't, everything else would be attracted to the Earth.
The force of gravity is dependent on two things. The mass of the object, so if we're thinking about a planet, exerting a force of gravity on things on the surface of that planet, the larger the planet, the greater the force of gravity. The larger, more mass of the object, the more force of gravity it will have. But also, the distance from that object. So if you travel in the next SpaceX mission into space, as you start to travel away from the Earth's surface, higher and higher in the atmosphere, what happens to your weight? Does it all of a sudden just disappear? No. Brian, what happens?
You start to you start to float.
Yes, and that happens gradually. The force of gravity, as you get farther and farther from the Earth, the force of gravity gets less and less until you completely escape the force of the Earth's gravity and you become what? Do you become massless?
No.
No. You still have matter that makes up your body, the same matter you had when you were waiting in the spaceship on your liftoff, so you're not massless, but you're weightless because the force of gravity is gone. Okay? So gravity depends on both the size of the objects and the distance from the center of the planet. So we'll look at some video in a few minutes of astronauts walking around the surface of the moon. Is there gravity on the moon?
Yes.
Yes.
Yeah, there is. There's less gravity than there is on Earth. Okay? In a minute. Oh, right there? What do you mean? All right. So, gravity on the Earth is what? Greater than gravity on the moon. Why?
Larger.
The size of the planet. Earth is much larger than the moon. Where did the moon come from?
Didn't some other planet crash into Earth and something came off the Earth? And
Yeah, scientists believe it came off of the Earth. So, gravity on Earth is greater than gravity on the moon, about 6 times greater. So a person's weight on the moon, on the Earth, compared to their weight on the moon, right?
Slightly more than.
Yeah, it's greater than their weight on the moon. How about mass? Equal mass. Person travels to a larger planet, let's say Jupiter. Force of gravity on Jupiter is greater than it is on Earth. A person's weight on Jupiter would be greater than it is on Earth, but their mass would be the same. Grace?
I have a question. So like, they call Jupiter like a gas planet. So like, it's still like a planet.
Yeah.
It's surrounded by it.
Yes, yes. Now, gravity also varies on Earth. We often don't think of it, but on the surface of the Earth, gravity, the force of gravity, can change, because gravity is dependent on distance from the center of the object. On a mountaintop, what's the force of gravity compared to at a valley? Well,
Last.
yeah, it's less on the mountaintop. It's farther from the center of the Earth. So technically, a person's weight should be less on the top of the mountain versus in a deep valley. Now, is it a measurable amount using our common tools? Probably not, but it is different. So in summary, your mass never changes dependent on location. I shouldn't say this really, never changes, because obviously people's mass changes as they grow. Okay? If they gain weight or lose weight, their mass changes. But if you have a certain mass, it's not dependent on location. But weight does depend on location. I don't really like that sentence. Should get rid of that. So the force of gravity on Earth is 9.8 meters per second squared. On the moon, it's 1.64 meters per second squared. About 1/6 of what it is on the Earth. So, if your mass on Earth is 70 kilograms, your mass on the moon should be 15,
70 kilograms.
also 70 kilograms. Your mass would not.
Oh.
So you gotta be careful. If we calculate it out, 70 kilograms times force of gravity on Earth is 797 newtons. On the moon, it would be about 1/6 of that, 115 newtons. Again, your mass doesn't depend on location, but weight does.
What's 1 Newton about?
What's that? You know, here is a spring scale. I'll show you. We often will use a spring scale to measure forces in Newton. This spring scale goes up to about 2.5 newtons. So if I put this is about 3 newtons of force. And so 1 newton is 100 grams on Earth. All right, it's kind of fun to watch people walking around in low gravity situations. So let me just show you these few videos here. So when astronauts first arrived on the moon, they had to sort of experiment a little bit. What's the best way to move around? You know, walking, leaping, running, hopping. And so they are experimenting a little bit here on their first travels, okay? Oh, I have to give it to you still. It's a worksheet. I'll give it to you in a minute. I'll pass it out while we're watching these. So here's someone, I don't know which astronaut this is.
Boy, when you do this, then you go down slope. That first step is the wrong one.
Looks like slow motion, but it's not. Why does it look slow motion?
This is the best way for me to
Ready?
travel, uphill or downhill.
Yeah, because it stays airborne so long, it seems like it's slowed down.
But see, in a level ground, I can skip. I don't like that loping thing. Loping's the only way to go. See, on a level ground, I can skip.
It doesn't have to, they're just an experiment. What's the best way to move
I
around?
cover ground like a kangaroo. Better here, measure height. You got all the cubes, you're coming out south. Verify heat flow is level and aligned. It is aligned, the normal is good.
So there's running.
UHT to the LRB, LMC speaks, and then what do I do? Let me see. It doesn't need to carry that UHT. Jack, I'm gonna leave the UHT. Give me heat flow in case you need it. Okay?
Oh, this one's kind of funny.
One distinct layer about 10%, which has multi-layers within it, and another at about 40%, which looks like a solid unit of a somewhat canter hard rock, but it's covered with fine tailor. And we have to see.
So watch as he walks away.
Further down.
This one's kind of hard to see.
Yeah, go ahead. Oh, there. Pour it over. Let me throw the hammer. Okay, let me throw the hammer.
He's going to throw the hammer.
Please. Oh, here. You got the
See, he's over here.
Here's John. You got to be able to throw. You ready? Go ahead. You ready for this? Ready for this? Yeah. Don't hit the lap. Or the out step.
Can't really see, you see it flying up there.
Look at that.
It goes,
Look at that.
you can see it goes flying up here.
Or the out step.
Oh yeah.
Look at that. Look at that.
So again, because of that lower force of gravity, you could throw something much higher, much farther than.
Being an astronaut must be so fun.
What?